Okay. I started my record, so we lost maybe the first slide of my record, but I will record these, and then as soon as I get them converted, I will upload them. I'll send you an email to that effect. Okay. So going back to bases, anything that produces the polyatomic ion OH negative, as I wrote on the board here, as you can see there on the slide, the hydroxide, that is a base. Okay. Now, in general, if you were to taste them, I don't recommend them, but they have a bitter taste. And solid form, they tend to be kind of chalky. Okay. Put them on your finger, you have to feel them with your hands. They'll feel kind of soapy and kind of slippery, and that is because it is actually breaking down the tissue of your skin. So you got to be very careful. Okay. All right. Getting some more colon. All right. Now going back to the litmus paper, as I explained for acids, there's the red litmus paper, and if you put this into a basic solution, it would turn it blue. So that's one way to identify what we have. And so for the definition, there's two types of acids. The first one is called the Arrhenius acid, Arrhenius. And the Arrhenius definition of an acid is anything that produces a proton. So in that reaction that you see up there on the slide, you see hydrochloric acid, same acid that's in your stomach. When it goes in solution, they will break apart. They will dissociate. And in one case, you find the H+, which is the proton, okay? And the corresponding cation, which here in this case is the chloride ion, okay? Now, for a base, an Arrhenius base is anything that produces the hydroxide. So we have on the left-hand side of the next reaction, sodium hydroxide. Sodium hydroxide is soluble in water, and when it dissociates, okay, it breaks up into the ions, corresponding ions, sodium plus, the sodium ion plus the hydroxide. Remember, this is a polyatomic ion. The OH remains together as a unit. Okay? The OH, they don't break up into separate oxygen and hydrogen. All right, now, the other chapters that we will talk about down the road are reaction types. This is an introduction of the first type of those reactions, and it's called the neutralization reaction. The thing to take away from this is that anytime you react an acid and a base, they neutralize each other, okay? And so if you look at that reaction, given there by the red arrows, you have the acid, hydrochloric acid, reacting with sodium hydroxide. And for any neutralization reaction, when the hydroxide and the proton combine, guess what they form? Water. Okay? You neutralize the acid and you neutralize the hydroxide ion to form water, denoted here by H2O. And then you got the corresponding salts of whatever they were. And so in this case, in this type of reaction, you form what we call a salt. Now, the thing about the term salt, we're all familiar with the term salt. We all think about sodium chloride as a salt, which is correct. But in chemistry, a salt is simply an ionic compound. We recall the types of compounds that we can make. One of them is an ionic compound, which is the result of a metal and a non-metal. So we have here sodium chloride, sodium being the metal, the chloride being the non-metal. Okay? We always form a particular salt. All right. Now, that was pretty good because sometimes when you react to form a proton or a hydroxide, but there was that had nothing to do with hydroxide. And so another definition had to be created. And the second definition is Lowry, acid base. Okay? Now, when we compare the definition, Lowry definition, they both share the same name as acid. They're actually where they differ is the base. In the Arrhenius example we just talked about, the hydroxide is what is created called Arrhenius base. But with respect to the Bronsted-Lowry, it is a base kind of chemical that will accept. So if you look at the reaction, you have HC on the hydrochloric acid, and HC, remember, is ammonia. Okay, and we did the structures of ammonia in lone pair and nitrogen. That proton actually combines with this lone pair to form NH4 plus, what we call, which is another polyatomic ion, the ammonia. Again, you can find that in the polyatomic ion table, the periodic table on the left side. That is a cation, a positive charge ion, and from the corresponding there's no hydroxide involved here. Okay, so again, brown similarity base, all right, so we have strong acids. When we talk about strong acids and strong bases, all we are talking about the extent by which they dissociate in solution. And the strongest you create all the ions. So examples of strong that means the additional three is only and that's strong because we associate from all out of solution. Okay? So that's when we talk about strong and weak, we're talking about percentage of solution. Okay, so hydrochloric acid dissociates totally, literally all protons and all chloride ions. Okay. Now, with respect to bases, here's two examples you should be familiar with. Is KOH, otherwise known as potassium hydroxide, and then NOH, which we talked about, sodium hydroxide. Now, they dissociate once you put in water 100%, therefore characterized as a strong base. Strong base. So here in that reaction, you have sodium hydroxide totally dissociated to form the ion sodium ion and the hydroxide ion. Okay, so when we talk about strong, that's what we're talking about. Now, how do we denote that in the diagram? If you look at the left side, that beaker, you have a solution of hydrochloric acid. They are totally dissociated. All the ions are apart and all dissolved in the water. Okay? Now, if you look at the diagram on the right-hand side, okay? Let me see. Francisco, you might want to video off. Okay? Check on your settings.
Turn my what on?
Your video off.
Oh, okay.
Okay, there you go, thank you. That way we'll get the bandwidth, not hesitate too much, hopefully. Okay, so on the right-hand side, you'll see that beaker, which is strong base, sodium hydroxide, and when they go in solution, totally dissociate. All the ions are separated, and they're all, they're all paired up. I got 3 hydroxides and 3 sodiums. On the left side, I got 3 protons and 3 chlorides. Okay. All right. So that's an example of a diagram what represents strong acid and strong base. Okay. Those are the acids I just talked about. You should be familiar with hydrochloric acid, nitric acid, and sulfuric acid. Very strong acid. And the only 2 bases that we're going to talk about up to this point would be sodium hydroxide and potassium hydroxide. Okay. And again, what does strong mean? Simply put, they totally dissociate 100%. Now, we have strong acids and strong bases, but we also have what are called weak acids. Okay. Now, if you look at HCH3O2, understood? You don't know what that is? I'll tell you what it is. So the examples we have a one-way arrow going from left to right. Notice that this one has a 2-way arrow. Okay. What that means is every reaction could proceed in both directions. And having that arrow because you're dealing with so when you put these acids in solution, they do not dissociate 100%. They could dissociate anywhere from 1 to 5%. It just depends on the acid. And up there we have some examples of some weak acid. HF, which is called acid. The next one you maybe H3 or maybe not, but you find that a lot in carbonated water. That's called carbonic acid. And then HC2H3O2. Again, that one's an example of vinegar. It's a form of vinegar. And the fourth HCP, that is called phosphoric acid. Again, that in a lot of objects. Okay, weak acid. Okay. So being a weak acid, they don't discriminate very much. How many you either together, ions are separate. A weak base, here's a good example of a weak base. And parentheses H2. may have some of the stomach when you turn out to the stomach, and you drink all that because it's into your stomach. It's a bit weak base. So we've been using ions to generate, and you got 2 hydroxide ions. Double arrow doesn't need. So that's right here. Let me see right now. And right here, this area right there. There a little bit. Okay, that designates the so that's solid. And up on top, you will find the ions. Okay, that are in solution. There are some ions in solution, not very many. Okay, the bulk of that material is still solid, and that's why milk and magnesia. If you ever look at that bottle, you have to take it and shake it up a little bit to drink it, because the bulk of it's insoluble and doesn't dissolve in water. Now, if you look at the example on the left side, you'll see that hydrochloric acid. Okay, we show that in the diagram as the white, but there are still ions that are in solution, designated by H negative. Okay, and it will, if we were to measure this with conductivity, it would give us a little bit of a signal. Times every signal, but nevertheless a signal. So that's how we designate with the diagram a weak acid and a weak base. Okay, those are the, for example, designated as weak acid, fluoric acid. It's like in staining glass. If you've ever seen glass, you use some of that. Carbonic acid, phosphoric acid, and then you have the weak base, which is many hydrogen. Okay, so it's kind of strong acids, traces, and acid, now weak acids, and weak. Okay. What does weak mean? When it's a weak acid, it just means that the compound has 100% and less than 5%. Okay. All right. Now, question here, you got a diagram they're asking you, which one would be the strong acid? Well, we analyze that diagram. Look at A. If you look at A, you see all the ions separated. So that would be an example of which is a weak acid. Yeah, you got that again, because they know strong acid. We can see that A and B have components that are still right there and right there. Okay, they haven't separated. Okay, so those can could be designated as an example of weak acid. Again, what is strong base? If you look at this, we can see we have hydroxide, and so there's no strong base out here. Okay, we have hydroxide. B could be anything, but obviously not an acid, not a base. Okay. Now, when we talk about acidity or alkalinity, we not so much from far to the side to 0 all the way up to 14. Neutral is 7. And anything less than 7 is acidic. Anything greater is and then in skills we can show that it's either something's weak acidic or weakly basic. For example, that's 12. Okay, strong base. Now we're going to introduce that here. It's kind of you see that we have proton. So the proton in represents is called the concentration. Okay, I'm going to use that in a second. We don't know about concentration. You know, things are more concentrated. You got volume over volume or a certain amount of this bracket is that is on the left hand side is when the proton concentration concentration in the middle, right here. When the proton concentration equals that concentration, and the concentration is greater than the base. Okay, now that's what we're going to introduce here right now. Basically, it has its own little name called molarity. Okay. So that in brackets is called molarity, and it has the units of moles over liter. So we don't have to worry about that right now, but later on we're going to be showing you how to calculate moles. Okay. And so the units are moles over liter, and that here down at the bottom, when the proton concentration is greater than hydroxide concentration, it's acidic. And then the converse is true, making it basic. Okay. Now, pH is nothing more than a mathematical calculation. Okay, it looks complicated, but it really isn't. Let's see if I can designate here. If it lets me. If we look up in here, you see a term called log. Okay, not to be concerned. The calculator has a button that is labeled log. If you have the concentration, you hit the log of that number, you get a negative number. But then if you notice up front, you have a negative in front of the log. Well, when you multiply a negative value by a negative, guess what? You end up with a positive. So the pH numbers are always positive, okay? And so down the next example, if you have a concentration of 0.1, and you take the log of that, you get the pH of a value of -1, multiply that by -1, you get a 1, okay? So something that's 10 to the negative 1 concentration has a pH of 1. Something that has a pH concentration 10 to the negative 5, guess what? Has a pH of 5. Pretty straightforward with these numbers. Something with a concentration of negative 8 has a pH of 8, making it alkaline. Okay, 5 is acidic, weak acidic. Okay, something that has a concentration of 10 to the negative 3 has a pH of 3, acidic solution. Okay, now if you don't have the 10 to the negative, you may be given 0.001. Remember scientific notation, convert that to scientific notation. That would be 10 to the negative 3 as well. Also has a pH of 3, again, acidic. And then here, if you convert that to scientific notation, now you have a pH of pH of 8. Okay, so alkaline. You notice that number is very small, 0.00000, so on all the way. That's a small hydrogen ion concentration. Obviously, you should end up with a high pH value. Okay. All right. Some examples of pHs to give you an idea. You got lemon juice. Around 2. Saliva, that varies. It depends on what you're drinking. Blood, very crucial pH. That could vary from individual, 7.3 to 7.4. Milk of magnesia, which is magnesium hydroxide, has a relatively high pH, about 11, 10 after 11. Ammonia, also alkaline, okay, and so forth. So that gives you an idea of what the pH values are, and you can relate those to real world items that you're familiar with. Okay, now with respect to buffers, the only thing we're going to worry about here with buffers is simply an acid and a base system that maintain a pH. Okay, it's a system that if your pH gets too acidic, it reacts with the base, bring that pH back to where you designed it. And you can have buffers in a variety of pH ranges. The most infamous one that we're all familiar with, or maybe we're not, but it's our blood system. We have to maintain a pH somewhere around 7.4. And we do that by our breathing of holding of carbon dioxide, and a variety of different things that occur because our blood system has to maintain that pH. So all a buffer does is a system of acid and the base that help maintain the pH of whatever pH you designed it for. Okay. Now let's look at this reaction up here. What we have here is nitric acid, HNO3, reacting with calcium hydroxide, very similar to magnesium hydroxide. Okay, and you recognize that you have nitric acid reacting with 2 hydroxides. So the nitric acid has 1 proton, and the hydroxide has 2 hydroxides. Okay, let me see if I can highlight that. So with respect to the protons, okay, nitric acid on the left has 1 proton in this formula. Hydroxide has 2 hydroxides. So this is an example. We got an acid in the base. This is an example of a neutralization reaction. Because there's 2 hydroxides, I require 2 nitric acids to neutralize that 2 OHs. So I end up creating 2 molecules of water. Okay. And then the corresponding salt, in this case, calcium nitrate. Okay. So in this case, they're asking you, who is the Arrhenius acid? That would be nitric acid. Because the Arrhenius acid is anything that produces the proton. That proton came from nitric acid. Therefore, calcium hydroxide must be the Arrhenius base. And asking you here, why is calcium bonded to nitrates? And remember, the nitrates are the polyatomic ions. Again, look at your polyatomic ion table. Each one has a -1 charge at NO3. Calcium is in group 2. When calcium becomes an ion, it's going to be a +2. So therefore, I need 2 negatives nitrates to balance the positive 3 charge of calcium. Okay. All right. So here they're asking you here, draw pictures of nitric acid, HF, hydrofluoric acid, potassium hydroxide, and magnesium hydroxide. Well, in order to do that, we have to recognize and define it first. Is it a strong acid or base, or is it a weak acid or base? So if you look at HNO3, guess what? From the list we gave you here, that's a strong acid. So that means that literally 100% of it will be dissociated. HF is a weak acid, okay? Now, 99% of the time when we write formulas, you're gonna find that hydrogen written first, okay? Like I draw there, it's kind of hard to draw, my fingers are too big, but notice I got hydrogen written first, okay? That's a good indication you're dealing with an acid. So if we look at a molecule like potassium hydroxide, guess what? We have the OH there. Again, good, especially bonded to a metal. We got that polyhydroxide ion. That is a base. And then finally down here, we can see again, OH with a metal, that's a base. So from that list we had earlier, the first one, HNO3 is a strong acid, HF was weak, potassium hydroxide was strong, and then magnesium hydroxide was weak. You have to define what they are first before you can draw a picture. Okay? Now, down at the bottom of the next slide, we're going to get in detail later on about solubility because that really defines a lot. But we know that nitric acid is a strong acid. So if we're to draw that, I need to draw it in this manner. Where I could, it doesn't matter how many units you put up there, but if I put 3 units of nitric acid, then I have to show 3 protons and then 3 nitrons, okay? The next one, HF, we know it's a weak acid. And so being weak, I got to show that I have some units that are still combined. And then obviously the ions with the charges to designate that it's a weak acid. Potassium hydroxide, by definition, strong base. So in this case, notice the slide. They're all separated. They're all totally dissociated. Now, magnesium hydroxide is a weak base because we gave you that. But we can also use the solubility rules down here in the bottom. And if we look under hydroxide, which is in the right column, you will see that any hydroxide, with the exception of what's bonded on the left side with number 1, is insoluble. What that means is that, yes, there's some ions that will be in solution, but the bulk of it, sorry about that, I went the wrong way. The bulk of it, again, do this again. The bulk of this material is still combined in 1 unit, and we designate it with a little hump there to show that everything's still together and insoluble. But then don't forget, we got to show that it is a weak base, so we have to designate the ions in solution. Even though it's insoluble, there's still a small amount of ions in solution. Okay. Now, summary with respect to acids. By definition, arrhenius acids are any chemical that make H plus or the proton ions in solution. Okay. Arrhenius bases are any chemicals that will make the hydroxide ion in solution. Okay. The other definition was the Bronsted acids. And those are defined as any chemical that produces or loses a proton, which is a similar definition to the arrhenius acid. That's what they have in common. Where they differ is how they define the base. In the Bronsted-Lowry base, that is any chemical that will accept that proton from that chemical that produced the proton. Okay. And then when we talk about a strong acid, that is an acid that dissociates to approximately 100%. So all the ions are in solution. Weak acids, much less than 100%. A lot of the acids are still combined, and we have a little bit in ions. With respect to bases, okay, strong bases dissociate 100%, just like the strong acid. And the weak ones, obviously, just like the weak acids, dissociate much less. Okay. much less. So buffers, all they do, it's a mixture of an acid and a base combination that maintain a pH constant to whatever pH you set that up for. Okay. Now, if there are any questions so far, feel free to type in the chat or something, and I can back it off, because we're coming in slide 22 of 34. Okay. Here are some more examples for you of soft drinks. Okay. Which brings me to a point. You notice that in the very first centuries, tap water has a pH a little bit greater than 7. That's alkaline. That varies from your water system. But think about this for a second. Some of you drink that alkaline water. It has a pH around 8-ish, 9. And then you ingest it. It goes into your stomach. And guess what happens to it? It neutralizes with your acid in your stomach. So you neutralize the alkalinity of the alkaline water as you drink it, making more water in your stomach and the corresponding salt, or whatever the alkaline is in that alkaline water. So, and there's some more examples there. Why is this important? Well, that's because this can happen. It will mess with your teeth, so be careful. Okay, which brings us to solubility rules. I introduced that table earlier. Okay, it looks complicated, but it really isn't. Okay, now with respect to solubility, something is either going to be soluble or insoluble. Now, even though it's classified as insoluble, remember there are some ions in solution. Okay, so we can use solubility rules to designate whether something is a weak base or a weak acid. Right, all the solubility rules take place at a temperature 25 degrees, roughly room temperature, because solubility just change with temperature. Okay, we're talking about ionic compounds. Okay, so if something is soluble, we can say that the compound dissolves or dissociates 100% completely. Okay, and we do that. We use the physical state of AQ, meaning aqueous solution. Okay, if something is insoluble, based on the solubility rule tables, then there may be a little bit in solution, but the bulk of it's still in solid form. And as far as the physical state, we designate that with the parentheses lowercase s for solid. Okay. Let's take a look at the solubility rules. All right. Notice in that table, again, you can find this table on the periodic table. So if you haven't downloaded that, you may want to download that, because you'll be using it quite a bit here. All right. On the left side, on the left column, okay, those are generally soluble when anything, number one, you have the lithium, the sodium, the potassium, and the ammonium. When any anion, anything with a negative charge, is bonded to any of those four, lithium, sodium, potassium, and ammonium, it is always soluble. Up to number one. And so if I have potassium chloride, potassium is there, soluble. If I have potassium oxide, soluble. Ammonium oxide, soluble. Okay? So let me erase that and go back. For number two on the soluble column, any cation that is bonded to the acetate, always soluble. Okay, so number two. So if we have copper acetate, potassium acetate, magnesium acetate, always soluble simply because it has the acetate ion attached to it. Number three, any cation, anything with positive charge, bonded to the nitrate, always soluble. Okay. The same is true for number four, with the halides, chromine, bromine, and iodine. Okay. Any cation that is bonded to those three is always soluble, except, and repeat, except these three right there: silver, mercury, and lead. X designates it either chloride, bromide, or iodide. So unless they are bonded to those three, they're soluble. But if they're bonded to those three, they are insoluble. Okay. Number 5, any cation that's bonded to the sulfate, SO4 -2, is soluble with the exception of 1, 2, 3, 4, 5. And that is potassium, I can't draw it very well, the calcium sulfate, strontium sulfate, barium sulfate, the silver, and the lead. If those sulfates are bonded to those 4 of them, 5 of them, they're insoluble. Okay? So that is for the column of potassium, soluble, excuse me. On the right-hand side, okay? On the right-hand side, starting, it says generally insoluble. Number 1, carbonate. Number 2, chromate. Number 3, phosphate. Okay? Those 3 guys. Any cation, okay? Any cation, anything with a positive charge bonded to those 3 are insoluble with one exception. If they're bonded to the big 4, if you will, if they're bonded to these guys. It's supposed to be an arrow. So if carbonate is bonded to lithium, sodium, or potassium, or ammonium, you're soluble. Otherwise, you're insoluble. Okay? The same is true for chromate number 2 and number 3, phosphate. If we look at number 4 on the right-hand side, that's called the sulfide ion. Remember that? -3 charge. It was in group 6. Sulfur becomes an anion, gets a non-metal, becomes a -2. Any cation, anything bonded, any positive charge metal that is bonded to the sulfide is insoluble except the guys in number 1, lithium, sodium, potassium, and ammonium, and let me see if I can get this guy here, and these 3 there. So you have 1, 4, 5, 6, 7 examples of sulfide ions bonded to the cation that are soluble. That means that everything else in the world that's bonded to is insoluble. Okay? And then number 5, the hydroxide. If they're not bonded to anybody in number 1 in the left-hand column, or calcium, strontium, and barium, if they're not bonded to those 7, they're insoluble. Okay? And that's how we use this table to tell us whether it's insoluble or soluble. And if it's soluble, then it's a strong electrolyte, strong base, or whatever the case may be. If it's insoluble, then it's weak. Okay? All right, so if we look at NaS, that example, sodium sulfide. Well, first thing we're going to do is recognize that sodium sulfide. Go find sulfide in the right-hand column, number 4. It says there that all sulfides are insoluble because it's in the insoluble column, except if it's bonded to the big 4 there, if you will, in number 1, or strontium, barium, or calcium. You can see it's sodium, so guess what? It's soluble. Hence, we write it down with the AQ. Aluminum hydroxide, next one in, we find the hydroxide, which is number 5 in the right-hand column. Everything bonded to the hydroxide is insoluble, except those exceptions. Therefore, aluminum hydroxide is insoluble. Okay, hence we designate it with lowercase s. Calcium carbonate. Well, we looked for the carbonate ion, which is in the insoluble column of number 1. It's insoluble, except those bonded with number 1 on the soluble side. Well, calcium doesn't belong there in that group, so therefore, guess what? Calcium carbonate is soluble. You find that around, you find a lot of, if you got calcium, a lot of calcium in the water, then carbonate, that's what you'll see, like if you got a ring around your tub, solid material. It's insoluble, that's why it doesn't dissolve very well. And you see your white powder. And then finally, potassium nitrate. The fact that you see potassium right up front tells you right on, don't even have to think about it. It's in number 1 of the soluble column, and therefore automatically soluble, hence we write it as AQ, aqueous solution. Go. Give me 1 second. Okay. Any questions at this point? All right, we're moving along to electrolytes. Now, electrolytes are nothing more than these atoms that have either lost or gained electrons, okay? And so if you're drinking an electrolyte drink, what you're drinking is the atoms that have lost or gained electrons, like sodium and the chlorides and so forth. Okay, so strong electrolytes, those are things that are soluble in water. They dissociate 100%, okay? They are good conductors of electricity. Why? Because they have the ions in solution. The ions in solution are the ones that carry the current. Hence, they're good conductors. Okay, so anything that's soluble, ionic soluble compounds, any of the strong acids or the strong base are strong electrolytes. So things like potassium bromide, nitric acid, I'm reading from left to right, potassium hydroxide, and sodium chloride. They're very strong electrolytes. The non-electrolytes, these are compounds that when you put them in water do not dissociate, okay? They stay intact. And most of the time, these guys are covalent compounds, okay? So water, when I put water in water, it stays H2O, carbon monoxide or carbon dioxide. When I put that in water, it stays, the structure remains intact. The C6H12O6 example, that's the general formula for sugar, okay? You put sugar in water, it does not dissociate into different components. It just goes in solution, okay? So these are non-conductors of electricity because no ions are formed. Okay? So if I were to put in pure water sugar, pure sugar, that solution would not conduct electricity, okay? Because there's no ions, no electrolytes, okay? Now, when we talk about weak electrolytes, either they're going to be a weak acid or a weak base, or they are insoluble based on the solubility rules. Okay. And so some examples we talked about, HF, which is hydrofluoric acid, magnesium hydroxide, insoluble due to the solubility rules. Okay. Silver chloride due to the solubility rules, insoluble. And the last one, carbonic acid, which was a weak acid. So these guys that are weak or insoluble create weak electrolytes, meaning that, yes, some electrolytes, they can produce some electrolytes, but not 100%. Remember earlier we talked about less than 5%. Okay, so question is, a strong electrolyte, let me see, come on. So if something is designated as a strong electrolyte, it's either going to be a strong acid or a strong base, or it's going to be an ionic compound that's soluble based on the solubility rules, okay? With respect to a weak electrolyte, it's going to be either a weak acid or a weak base, or based on the solubility rules, is insoluble, okay? And then a non-electrolyte is anything else that's a covalent compound. They do not form ions at all when they go in solution. Okay, so that's how those are designated. Now, this particular diagram here is basically we got two probes in the water solution, okay? And you can see from the top one, because we have, oh, let me back up, sorry. Because we have electrolytes in solution, which are in here designated by the negative and the positive spheres, okay? Because the electrolytes are there, that current passes through that wire on top. The bottom diagram, those are covalent compounds, okay? Non-electrolytes, they don't conduct electricity, and hence they don't close the circuit, so there's no electricity running through that wire on top. That's what we're talking about. Now, if we look at the diagrams, and we're back to diagrams, and we want to designate that either as a strong, weak, or non, we analyze the pictures. Okay, if we look at the one on the right, on the first one, we can see a big chunk of material sitting at the bottom of the beaker. Okay, but there's some ions still in solution, but the bulk of it's down at the bottom. That represents a weak electrolyte, weak ions. We see here that we got hydroxide. Okay, that further tells us, hey, it's a base. And so that on the left tells us we have a weak base. Okay, now over here, the one in the middle, that by the way is the formula for methane, CH4. All we see there's carbon and hydrogen. So that means it's a covalent compound. Being a covalent compound, it's not going to break apart. And so that water, that material, that methane gas in the solution is not ionic. It's a non-electrolyte. Then the final one, we see ions, paired ions all over the place. Nothing's recombined. They're all, there's 4 units there of the chloride and potassium. Okay, that would tell you that since none of those are combined, we get a very strong electrolyte. Strong electrolyte. So let me back up for a second. Strong electrolyte on that. Okay, so on the left, magnesium hydroxide. 1 second, we're getting some more people coming in. We got a weak electrolyte, magnesium hydroxide. We have a non-electrolyte, which is NH4 in the middle, and then potassium chloride, very strong electrolyte. Okay. Now here we had a list of compounds, and what they want you to do is to designate it as strong, weak, or non-electrolyte. Okay. Well, the non-electrolytes are probably the easiest because what do we say about non-electrolytes? They're nothing but covalent compounds, okay? Covalent compounds. And so we can go through this list and find the covalent compounds very quickly, okay? Because covalent compounds, as you recall, are those compounds that are made up of nothing but non-metals. So if you look at number 5, we got carbon dioxide, and then we look at number 8, you may not know what it is, but we just see that you have carbon, hydrogen, and oxygen. That's it. No metals involved. So that would tell you right off the bat that I have nothing but covalent compounds there. Now, what can be confusing is look at number 4. Okay, H2CO3. By that definition, all we see is non-metals. You can say, oh, we got a non-metal. But remember, 99% of the time when we're dealing with an acid, we put hydrogen up front. You see H2 there? Even though it's all non-metals, with hydrogen being up front, that should tell you, oh, hey, I'm dealing with an acid. Acids are the only example of covalent compounds that dissociate when they go in solution. Okay, that's important to get. Covalent compounds, 99% of the time, do not dissociate. The only exception is acids, like nitric acid, carbonic acid, phosphoric acid. Those examples we did before, okay? Those are covalent compounds, but because they are acids, and that's designated by the hydrogen written first, that should give you a flag to say, I'm dealing with an acid, okay? So number 4, covalent, but it's an acid. And then go back to your list of, is it a strong acid or weak acid? Well, that is a weak acid, okay? I don't see any other acids up here. So the rest of them are ionic compounds, okay? The rest of them are ionic compounds. And we utilize the solubility rules to determine whether it's strong or weak, okay? Now, if you go look at the solubility rules for number 1, barium sulfide, you will find it to be soluble. Therefore, barium sulfide is a strong electrolyte based on the solubility rules. Number 2, which is silver chloride, look that up in the solubility rules, you'll find it to be insoluble, which then tells you being insoluble, it is a weak electrolyte because the bulk of it's still in solution, but there are still some ions in solution. And then number 3, potassium. The fact that you see potassium written first automatically tells you this thing is a strong electrolyte because potassium is one of the 4 in this soluble column that are always soluble. Okay. We talked about number 4, carbonic acid. That's one of the weak acids we gave it. Okay. Therefore, it's a weak electrolyte. Number 5 we talked about, it's covalent, so it's a non-electrolyte. Number 6, sodium hydroxide. In fact, you see sodium written first based on the solubility rules, automatically strong electrolyte. Okay. Calcium carbonate, if we look up carbonate ion and the solubility rules, we'll find it to be insoluble, therefore designated it as a weak electrolyte. We talked about number 8 already. It's all you see is nothing but non-metals, therefore it's covalent and therefore non-electrolyte. Number 9, right off the top, you got sodium written first, automatically it's soluble. It's one of the 4 of the soluble, number 1 in the soluble column. Okay, therefore being soluble, it's strong. And then finally, number 10 is a sulfate. Normally anything bonded with the sulfates are soluble except those heavy metals that we mentioned, silver, mercury, and this guy, lead sulfate, therefore very insoluble. Okay. All right. Guess what, guys? You knocked out chapter 9. So I know it kind of went through it a little faster than normal, but given the circumstances, how we doing this, I'm kind of learning myself. I am open to suggestions. Trust me, if you want me to go at it a different way, send me an email, say, hey, Dr. Fay, why don't you try this? I'm more than happy to try anything right now. So this puts us at the end of chapter 9. I'm going to stop recording now, and it will get converted to an MP4, and then I'm going to shoot it up to the YouTube channel, and then make it available for you if you want to come back and review what we talked about. So